All right, so now that we've talked about one-factor ANOVAs, let's talk about two-way ANOVAs. So this is when we have multiple variables. In other words, now we're testing two different things at once. So before we might have had multiple groups, but we were still just testing one drug dose. We still only had one variable we were changing, just multiple groups with that. Here we're actually comparing two different variables at once. And within that, you have multiple treatments within each variable. So for example, let's take a look here. You might want to measure tumor vascularization, so in other words, the amount of blood vessels that grow in the tumor after various treatments on different tumors. So now we have two variables here. We have our different treatments, all right, so that's one variable. What drug is being added is a variable. But also we have different tumors. So maybe a brain tumor is different from a colon cancer and so forth. So we have the variable of the tumor type and the variable of the drug treatment. Right, so if we take a look at this, we can see here that we have a control-treated tumor. We have the drug Avastin, the drug thalidomide integrin antagonist. This is one variable. But we also have the control tissue and different glioma, brain tumor type cells, and breast tumor. So this is another variable. So we might want to find out, one, do these drugs make a difference on these various tumors? But we might also want to know if the tumors are different from each other in their amount of vascularization. And third, we actually can find out if some of these drugs are better for one tumor type and another drug for a different tumor type. And that really is seeing if it makes a difference which drug we use based on which tumor we are treating. So that's kind of talking about, is there an interaction between variable 1, the type of drug, and variable 2, the type of tumor? Does certain drugs work better on other tumors? Is there an interaction? So we're really looking at three different things. All right, so let's come back to that in a second. But one of the requirements for a two-way ANOVA is that we need equal replicates in each group. So we were able to get away with unequal replicates in the one-way ANOVA because we just kind of selected all the replicates and Excel naturally ignored the empty cells. But for a two-way ANOVA, we absolutely have to have equal replicates because of the way this is all set up. Right? So what if you don't have equal replicates? Well, you can either randomly remove extra replicates in larger groups, or you can estimate values for the other groups to kind of make up the extra missing data points. Obviously, you cannot do that. You never should be making up data, so you can remove the extra replicates. So if you have 6 replicates in one group and 4 in another, you would remove 2 replicates from the one so that you're analyzing 4 replicates each. But it has to be random which ones you remove. You cannot pick the ones that are the high or the low or the ones that don't make sense to you. You have to randomly pick the ones that you remove using a random number selector. But that way, you can reduce a couple replicates so that you have the same replicates because, again, the two-way ANOVA requires that we have equal replicates in each group. All right, so I talked about the 3 general hypotheses. We can find out if our drug works. So which drug works the best is one thing, a question we're asking. What tumor has the most neovascularization? And is there a difference based on which drug works best for which tumor type? So in other words, is there an interaction between these two variables, right? So when you're testing statistics, you're always looking at the null hypothesis. So we actually have 3 general hypotheses, meaning we have 3 null hypotheses. Null hypothesis number 1, there is no significant difference in tumor vascularization based on the drug treatments. All right, so we're looking at this variable alone. Null hypothesis says there's no significant difference. So that would mean that if we reject the null hypothesis for that one, we are saying that there is a significant difference. At least one of these drugs worked better than the others, or was different than the others at least. So based on that, we also have this variable here with the tumor type. There's no significant difference in tumor vascularization based on the type of tumor. Right? So again, if you reject this null hypothesis, it means that one of these groups, maybe one of the tumors, has a different amount of vascularization from the rest. Then our third variable, our third hypothesis talks about the interaction. So our third null hypothesis would simply state there is no interaction between variable A and variable B. So in this case, variable A being our drug treatment and variable B being the type of tumor. So if you reject this null hypothesis, it means there is an interaction, which would tell you that the type of drug that works best is dependent on the tumor. So maybe some Avastin might work best for glioma, but integrin antagonist for the breast tumor. So again, we always have three null hypotheses that we're testing in a two-way ANOVA. We're testing if we're saying there's no significant difference in variable A, that's one null hypothesis. No significant difference in variable B, second null hypothesis. No interaction, third hypothesis. Right? So within this, we are going to go over the two-way ANOVA data. This is still an ANOVA, so we still need to make sure the variances are close enough to equal. So just like in the one-way ANOVA, we need to calculate the F max and F max critical. Right? So then the key aspect for doing this, it's actually pretty easy to do this in the two-way ANOVA on Excel, but you have to organize the data correctly. And I'll show you how to organize the data and what this means. So one of the variables has to be in the columns, the replicates within those columns, and the second variable has the rows above and below each other. And this will make a lot more sense when we see this on the Excel. What I want you to be able to do from this, you should be able to generate two-way ANOVA data. So in other words, you should be able to use Excel to get the two-way ANOVA statistical analysis. And that means you have to be able to set up the data in the appropriate way in order to do this. And then once you get that statistical analysis, you should be able to interpret it. So you need to be able to know what your three null hypotheses you're testing are, what the two-way ANOVA statistics tell you about that, and what that means in the real life. All right? And so within all of this, just like within the things we've done before with parametric statistics, you should do this on the Excel file. There's also questions on the Word document file that you should answer. And once we go through one tab on the Excel file together, you should be able to do the other one on your own. All right, so let's take a look at this set of data here. So this is from an experiment that we actually do in advanced cell biology, where we're looking at the effects of the drug staurosporin on the formation of stem cells, two different types of stem cell colonies. So we have erythroblasts and granulocyte monocytes. So we basically have our situation for a two-way ANOVA here, because we have two variables. We have the type, the amount of drug, variable 1, and then we have the type of colony, variable 2. All right, so just like with the one-way ANOVA, we need to first make sure our variances are close enough so that we can continue on with this parametric stat, because the ANOVAs always assume that the variances are equal. So if you remember, since we have multiple groups, we're doing the F max calculation. So the F max calculated is the highest variable over the lowest variable. So if I'm going to calculate that, I would find this here, that my highest variance is 63. I think I said variable, but the highest variance divided by the lowest variance, sorry. And so I'm going to divide that by my lowest variance, which is this value right here. I think there's two of them that are the same. But that gives us a variance that's pretty darn high. But let's take a look at the table for a second, because we know that for the table we need to know A. That's our number of groups. We have 8. 1, 2, 3, 4, 5, 6, 7, 8. And our degrees of freedom is 3, because each group has 4 replicates. 4 minus 1 is 3 for our degrees of freedom. So if we go to our table here, we know we're looking at 8. This is the F max table. 8 for our number of categories. And our degrees of freedom 3 is 83.3. So this is a pretty high number because we don't have many replicates, so it knows that we are probably going to have some high degree of variation. And so basically we're fine. Our F max calculated is less than our F max critical. We're good to go. So how do we do this two-way ANOVA? I've set it up perfectly here for you already. What we're trying to do is get our types of colonies. All right, so one variable has to be in the column. So all my E's need to be in one column and all my GM's need to be in another column. And then the other variable stacks right on top of each other. So all the data from 0 nanomolar staurosporin is going to go here. And then right below it will be our 10 nanomolar staurosporin, and then 25, and so forth. So again, you have to have the variables in one direction. So our E and GM variable, our type of colonies, is 1. And then from there, let's think about this. So we can take the data for our 0 nanomolar staurosporin from E, and we have to put that right there. But then the rest of the E has to go right below that. So I have to put my E from 10 right below that, and then my E, and I have to make sure that I'm not accidentally including the average. I almost made that mistake right there. I'm only including the replicates. So I'm going to do the next 4 for the 25, and I'm going to put it right underneath that, and then I'm going to do these last 4 here. So now I have all my E's in one column together, and these guys would be for all of this would be for the 0 staurosporin. So I can take these cells and I can merge them, and I can just kind of label it as the 0 nanomolar staurosporin. Let me spread this out a little bit so we can see it. And then I'm going to merge these next 4 because I need to make sure that they all have the equal number of replicates. They're all in the groups of 4. So I'm going to merge and center that. There's my 10 nanomolar staurosporin group. I'm going to merge and center these next 4. That should be my 25 nanomolar staurosporin group. And then these. All I'm doing is showing you how I set up this table that I had already set up, because to do a two-way ANOVA, you have to take the data that's usually going to be in this type of format and put it in this type of format. All right, so now I can get my GM colonies, and again, they have to be one stacked right on top of each other. So there's my 0 nanomolar staurosporin, so it has to be where those rows are at. And then I can get my next ones right underneath that. And then I can get my next ones right underneath that. And then finally my last ones right underneath that. So all I did is I just reorganized my data such that all of the replicates for E were in one column, all the replicates for GM were in the second column, and then they were stacked right on top of each other. 0 nanomolar staurosporin was here, then right below that 10, and all of my groups kind of stacked on top of each other. And the reason that you have to have equal replicates is because it's going to take this data and you're going to tell it that there's 4 replicates, and so it's going to start here, and then it knows that after 4 it's doing the next one. After 4 it's doing the next one. So now that we have that, the two-way ANOVA itself is actually really easy. I'm just going to go to Data, Data Analysis, and I'm going to go ANOVA two-factor with replication. And I am going to choose all of my data that I have, and I'm going to include the labels. Always include the labels here. Right? It doesn't even give you the choice here. You have to include the labels. And then you're going to tell it rows per sample. That basically means your replicates. I have 4 rows per sample. 1, 2, 3, 4. That's my number of replicates. This is saying we want a 95% confidence interval. And then I'm going to give myself a spot to put the table. And when I do that, this comes up here, and it tells me some data based on my groups of staurosporin. But this is what I'm looking for down here. You have to remember which variable you put into the columns. So columns is right there, and my columns means the E and GM. So my columns is the type of colony. So my p-value for the type of colony is way under 0.05. That means there is a significant difference between the types of colonies in these stem cells. So if columns is the E and GM, then sample is the staurosporin dose, and there's certainly a significant difference between the staurosporin dose. The staurosporin makes a difference. So we're rejecting the null hypothesis that there was no difference based on staurosporin. We're rejecting the null hypothesis that there's no difference in the types of colonies. And then the last one is the interaction. We're actually rejecting the null hypothesis that there was no interaction. What that means is that the staurosporin appears to work better or differently on the 2 types of colonies. We can kind of see that. Initially, we had about the same number of E and GM colonies, but as we added staurosporin, they affected the E colonies at much lower dose than staurosporin affected the GM colonies. So the staurosporin did indeed have a different effect depending on which type of colony we were talking about, and therefore there is a significant interaction. We rejected the null hypothesis that there's no interaction. And when I say rejecting the null hypothesis, the p-values are working the same as we've seen before. If it's under 0.05, we reject the null hypothesis. There's a less than 5% chance that the null hypothesis is correct.